So I can start introducing this part, the advanced course part, which is a step forward in geological mapping. So you have done so far, or the people that have already done some geological map before on planetary bodies know how traditionally have been done. And now we want to give you a flavor of some advanced products on how they can be done and the idea behind these products. So as you have seen during the basic part of our school, you have seen that most of the geological mapping that you have done is based on black and white images with some additional informations with DTMs. Now there are even some colorized images, RGB, that can help, but mainly from the beginning, from the first map of 1960 by Schumacher, and afterwards, the most of the geological maps that have been done were based on photogeological interpretation on black and white images. So as already shown by and said during the base course by Monica, it is clear that we should improve this map a bit to look them more similar to the geological map on the Earth. So we started a program, the European program, H 2020, that has the aim to integrate data from different sources to generate a high-level geological product for the exploration of the Moon, Mars, and Mercury. You see to the left, and you know already that we may have different products beside the images. So the spectral cubes that say us something about the spectral property of the material, and they can be related to spectral, I would say, response and mineralogy. And then we can have geophysical data like the radar sounder data. And then we can even use all our maps in order to create 3D geological model as we normally do on Earth. So the idea is to improve the classical and traditional way of doing geological map for gaining high-level products. And this was done by plan map on Mercury, Moon, and Mars that were the main subject even of the base school. So we had also to prepare the toolboxes and some pipelines in order to produce these products, these new maps and derived products, in order to use them for future robotic human mission and fill the ESA database. And then we would like to provide 3D geological models and virtual reconstruction that will be virtual reconstruction with the subject of the Cassini's meeting. So our main idea was to go forward in two parallel ways. So in one way, on the top, is to use the geological map that we may have produced, even considering the possibility of retrieving the dip and strike of strata in order to create 3D model of planetary bodies. So this is a way of improvement of the geological map to an higher level product. Then there is the second way, that is to start with a traditional morphostratigraphic map derived by photogeological interpretation, use even absolute model ages in order to have a well-controlled stratigraphic chart in terms of absolute model ages, So put numbers here on the relative ages, and then use this map and integrate them with the information from spectral indexes derived by cubes in order to have new maps that integrate the morphological information with the lithological or compositional information, or at least the spectral behavior of the material on the surface. So these maps are much more similar to the Earth ones. Even this map can eventually be a base for creating 3D geomodels, but we have not still there. And the idea at the end is the one that you see here to the left. It's the, I would say, the main frame of background our presentation. The idea is to create a way for any kind of human or rover missions to any kind of planet to look to a landform and see how the geological map, the landform is fitting to the geological map, and see even underneath the surface. So you may imagine a future astronaut looking to a landscape on Mars, on the moon, and understanding already that which could be the subsurface of that area. So the geology of that area. So it's very ambitious, this last point, but we have to go through all the others. So the 3D geomodel and the integrated maps between classical morphostratigraphic map and information derived by spectral indexes. So that's why we are going to the advanced part of geological maps. And we will start with the crater chronology. So how the surfaces of a planetary body can be dated in using the crater density. Lucia has already told about it, and in a few minutes, Harry will explain it widely. And you will do a practical activity on it tomorrow. Then there will be a practical activity about the integration of morphostratigraphy with spectral information. So you see here to the left some morphostratigraphic map, spectral map, so spectral indexes, images, and all together will find the way to arrive to an integrated map. Then there will be the 3D geological modeling. Here we see some 3D models of Mercury, Mars, and on the moon. In order to do the sorry. And in order to do the one on the moon, we have to use the radar, so geophysical data. And you will perform some experience also on that. So here we see the moon with the radar and some interpreted 3D surfaces, but you will probably, we will use radargrams of the polar cap on Mars to do such 3D geological models. Then you will even have some experience on what are 3D models of in situ observation. We know that we can derive models, so 3D models of what we observe with the rover, and they are called digital outcrop models. And from that models, you can even retrieve some geological information, and you will see how to do. As I said, as Angelo said during the base course, the GMAP activity is aimed at supporting you on planetary mapping or producing high-level products with different way. You see that we have the web page, wiki, we have GitHub for the tools that we may produce, and some has been already produced by PlanMap. And then there will be possibility for data access and discovery, and cloud services, and other possibility for tools development. We have already seen and explained during the base course that there are different ways for publishing your geological map. The most important one is the USGS, and the most historical one is the USGS program of geological maps. But there are even journals on which you can publish your map. Normally, when you do your map, they could be in support of your scientific paper, but in that case, you have just a figure, just a figure there that cannot be used by someone else. So GMAP want to collect the map in WebGIS and be useful even for other people. And in the same time, we would like to favor the publication of maps specifically on journals that are, I would say, dedicated completely on maps. And these journals are the journal maps and the journal field trip and maps, together with the USGS program. So the journal map is a journal that publishes all kinds of maps, as you see there. So even the political maps, social maps, it's not strictly dedicated to geology. The journal field trip and maps is strictly dedicated to geology, and it's a journal that is published by the Italian Geological Society and the Italian Geological Survey. And we, as GMAP, we have an agreement with this publication. All this way of publishing geological map are not strictly associated to strong impact factor, but they are the only way for publishing map in a professional way, because we need a professional way of producing geological maps, and these three are the three ones. I would say journal maps has some impact factor. The other ones, no, but USGS, it's historical, the most important reference for geological maps. And the geological field trip and maps, as I said, it's completely dedicated to geological maps. And it's another possibility, in particular, if you want to publish innovative map and not the traditional ones, or not only the traditional ones. So having said everything on it, I would invite you to try a step forward into geological mapping, starting with the presentation of Harry about crater chronology. And afterwards, tomorrow, you will work practically on the application of these methodology. So I would leave now the stage to Harry, and I stop sharing.
Okay, thanks, Matteo. So I think you need to give me permission to share my screen.
Sorry.
Okay. Okay. So welcome back. I think you already had a pretty long and hard day, so I really appreciate that you are sticking around for this presentation, which is entitled Absolute Model Ages from, and here I changed the title, from crater size frequency distribution measurements, because the original title on the program says Absolute Model Ages from crater counts, and that's always a